Thank you. It's a new look I'm going with. I think a little geeky nerdy. So yeah, that's what we have right now. So today we are to do finish this chapter. Took a little longer than expected, and at the same time I have to discuss with you guys past paper questions, right? So we'll do this in two parts. First the remainder theory left, and then the past paper questions. All right, that works for you? Yeah. Mm-hmm. 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 Okay, so let's start. Where are we at? So let me share my screen now. Hey everybody. Yep, you see the screen now. Okay. All right. Back in action. We are back in action. Okay. So, what are we starting off with? So this is the third lesson in Equilibria and how some factors affect Equilibria. That's the last thing we did last time. And I have it written down, Arisha. I don't remember right now. I don't know. I forgot. I have it written on if that's something that you guys need to know right now. Okay, yes, I can tell you what I'm planning to do next. And if somebody wants me to change something, I can do that also. Yeah. So what I was intending to do was change in concentration, changes that. Yeah, organic chemistry. We can start organic or we can start atmosphere. That's where I'm at right now. Yes, we can do organic. Absolutely, we can do organic. And so that's what we'll start. All right. Yeah. So you go with organic, you all go with organic. Okay, so let's continue right now. We'll talk about organic later, right? Yeah, we have that. We have participants, we have Q&A, and at the same time we have participants, Q&A, and what else? Yeah. All right, so let's continue. तुमने क्या बात की थी? Yeah. So equilibrium and its factors, the factors that are affecting equilibrium. And what factors are affecting equilibrium? So factors that affect equilibrium. Equilibrium. And we did the first factor, that was concentration. Then we've got to talk about how pressure and how temperature affects equilibrium. Those are this, yeah. Arisha, we did the extraction of metals for iron at least. Then electrolysis करेंगे electrolysis अभी after organic, ठीक है? And that's it, yeah, ठीक है? So the factors that affect equilibrium were, I was saying, concentration. It's concentration, pressure. Okay. You could say temperature. You know, these are also factors that affect rate. But there are some other factors that affect rate but not affect concentration. So concentration affects rate and equilibrium, pressure affects rate and equilibrium, position, the equilibrium position, temperature affects the rate and equilibrium position, and there are two other things that affect rate but not. So concentration affects rate and equilibrium, pressure affects rate and therefore equilibrium, temperature affects rate and also equilibrium. But there are two other factors, which is particle size, which is surface area, particle size, and catalyst. These two factors are the factors that affect rate, but not equilibrium position. Because remember, the reason why even equilibrium is affected is because of the change of rates. But there are two of these factors that are affecting rate but not going to affect equilibrium position. So the last time we discussed how concentration affects rate. The principle that depended itself on was called Le-Chatelier's principle, and the idea was simply that whatever change is externally caused to a closed equilibrium system, the equilibrium shifts in a way to oppose that change. That's what an equilibrium does. All right. Now, that's something that you got to keep in mind, and that relationship is important. So basically, any effect that any external effect that is brought upon a closed equilibrium system, the equilibrium shifts to oppose that, change, that effect. So if we had remembered last time we did, if we change the concentration of one, or if we increase the concentration of the left hand side, the equilibrium will shift to the right to decrease the concentration of left hand side. If you increase the concentration of right hand side, the equilibrium shifts left to decrease the concentration of the right hand side. That's what we were looking at. That's what we did that. All right. Then that's the part we've done so far. Any questions from this, guys? Last time की तरह कोई सवाल हैं इसके बारे में? Before I can continue. No, okay, all right, ठीक है. Now, the second factor we're going to talk about is pressure. But one thing to discuss about pressure is that pressure only affects gases. So pressure only affects gases. Okay? And one thing you need to know is that pressure is proportional to the number of moles of gas. What that means is, literally, if there are more moles of gas in a system, the pressure will be higher. Because, one thing to note that is that, technically speaking, pressure comes from bombarding along the walls of the container. Alright? So what I mean is that if this is my container and I have gotten myself some, let's say I have 4 molecules right now, 5, and I'll duplicate this. So I'll bring this here and I'll bring this here. Now, on the left hand side, I have more molecules of gas. On the right hand side, I have fewer molecules of gas. Yes, I'm good. I know. I'm a little. Yeah. I need to. I don't know. Some days, if I'm doing something right at the cut of class and I just get in the class, it just becomes very haphazard, and I am not really well set. Like today, I don't feel like I had enough time to like get my mind ready for this class. I need like generally because I was busy setting up the whole thing and my lights and my um, yeah, that kind of stuff, lights and this and that. Yeah, so that's why. Yeah, you know. Like for example, this is what I'm seeing right now. I'll take a picture of you guys. I'll take a picture of you guys. That'll be nice. I don't know why I'm taking a picture of you guys. Yeah, anyways, sorry. It's just that kind of way. Alright. I don't know, it's just the... Alright, Arisha. It has been. Hey guys. It has been, really been. Yep. It has been. Absolutely. Yeah. Alright, so where was I? So in these two particular systems right here, what we have is that on the left hand side you see more molecules of gas than the right hand side. Yeah. So Abhi, I'm teaching you just the factor and then talking about how the factor affects rate. Right now I'm showing you two scenarios. Let's call the scenario A on the right hand side and scenario B on the left hand side. So in A, since you have fewer molecules of gas, they are also moving randomly, remember? They are moving randomly. And these are molecules of gas. So in any system, the pressure of the system is given by the frequency of bombardment of those particles along the walls of the container. So here 5 particles are bombarding along the walls of the container. The problem is that on sorry, not the problem, but the difference between that and scenario B is that in scenario B, you have a lot more molecules moving around. What that means is a lot more molecules are bombarding the walls of the container. So if I were to ask you which of the molecules are causing more bombardment along the walls, what would you say? Which of these have more bombardments per second along the wall if all the molecules are moving at the same speed? It's pretty obvious that B, right? So B has more bombardment. Therefore, it generates greater pressure. All right? So if I want to reduce pressure of B, one of the ways to do that would be to open the container and let some of the molecules move out, right? Because then there'll be fewer molecules and fewer bombardments, right? Yeah. Bye, Sarah. Long time, I know. It's been a while. Yep. I forgot, were you always attending O-levels or what? I forgot where we met. The Sarah on YouTube, I don't remember. But I remember you by the name very well. I forgot which class it was. But yeah, thank you. Thank you. It's a gift from a friend. Anyways, guys, sorry, I got distracted. Any questions about this, guys? Yes. Okay. All right. Okay. Yes, Sarah. All right. Haven't seen you in a while, but now you're back. So, moving along. My coffee is habza. Now maybe. Arisha, I've only had 1 cup of coffee today. I normally have them in the daytime. So, oh, A levels. Okay. All right. Okay, so guys, let's continue. Sorry. So why am I telling you this? I'm telling you this because a good way for an equilibrium, let's say for example, this is the rule for pressures. So if your equilibrium exists of gases, okay, and externally the pressure, if the pressure is increased, so if externally the pressure is increased in an equilibrium, remember the equilibrium's job will be to oppose that chain. So if externally your pressure is increased, okay, then if externally pressure is increased, then the equilibrium will shift to decrease pressure. Now that's important to know, and you got to keep this scenario in mind. Which scenario will the equilibrium want to decrease pressure? B or A? If I were to ask you guys. I'm glad you like coffee now. Yeah? Thank you, thank you, thank you. B. If I want to, no. See, you guys, let's listen to the question again. You know? Wait, I'm getting there now. Ukti. But the rest of the people, listen. I'm saying if externally pressure is increased, the equilibrium will do the opposite. We want to decrease pressure. Now, if what scenario will the equilibrium try to be? I'm not saying externally. Equilibrium will try to decrease pressure. It's going to decrease pressure by wanting to become this. If equilibrium wants to become this, it means the equilibrium wants to increase pressure. But to oppose the external factor, the equilibrium has to do the opposite. If externally pressure is increased, the equilibrium will have to shift to decrease pressure. And so that's where okay. All right, Sarah, bye bye. Okay, the rest of you following this? So meaning if the external party does this, the equilibrium will want to become this, the opposite. If the external party reduces pressure, the equilibrium will want to increase pressure. Because opposing that change is what Le-Chatelier's principle is. So you can learn this. So the basic principle is this. If externally pressure is increased, the equilibrium will shift to decrease. Le-Chatelier. Le-Chatelier. Yeah. And I'll spell it out for you later. You can Google it also. But so far, that's what I'm saying. Is that if pressure is increased, the equilibrium will try to shift to decrease pressure. Remember that. The equilibrium will want to decrease pressure. That's the thing. Now, how does equilibrium decrease pressure is what we want to discuss. So let's say that's the thing. So if I bring this here, that's what a system wants to do. If external pressure is increased, equilibrium want to shift to decrease pressure. And basically this is what you need to know, that pressure is proportional to the number of moles of gas. So if something wants to decrease pressure, all they have to do is decrease the number of moles of gas. Because if you decrease the number of moles of gas, you are going to decrease pressure. And that's what you got to remember. All right? So now, for example, okay, I'm actually going to give you the little diagram right now. Come on. Okay. So where is that? So if you remember, there was an equilibrium between nitrogen and hydrogen. Yeah? To make ammonia. Let me show that to you right now. So this would be a way to represent nitrogen and hydrogen forming ammonia. So you got nitrogen and hydrogen forming ammonia. It's like 1 mole of nitrogen and 3 moles of hydrogen are making 2 moles of ammonia. Now, understand that the left hand side has more moles of gas than the right hand side. What I'm saying is this, that in this particular scenario, this is important. Let's say you achieved equilibrium. They're in equilibrium, we don't know how much, but they reached equilibrium. Now after reaching equilibrium, if pressure is increased, so now if pressure is increased externally, what will the equilibrium try to do? The equilibrium will try to decrease pressure. This is Le Shortlist principle applied. If pressure is increased externally, the equilibrium will try to decrease pressure. And how can it decrease pressure? By the previous relationship. So if equilibrium wants to decrease pressure, what should it do, guys? Decrease the number of moles of gas. That's something that you got to remember. So if external pressure is increased, the equilibrium will try to decrease external pressure. How? By decreasing the number of moles of gas. Yeah? So which side has fewer moles of gas? That's where it will shift to. So it shifts to the side with fewer moles of gas. Which side is that? Anybody? So this Le Shortlist principle be applied vice versa? I don't understand the question, Saad. What is vice versa? And please, anybody writing a question, you please share to panelists and attendees. Okay? I don't follow your question, Saad. So the idea was that it should shift to the side with this fewer moles of gas. That's the ammonia side. So you'll say it shifts to the right hand side, which means more yield. That's what it means. We already discussed, remember, that pressure increases rate, but now pressure also increases there. In this particular case, pressure will move this equilibrium to the right. Yeah? And obviously, if the pressure was decreased externally, the equilibrium will move to increased pressure. Yes, Saad. So if the pressure is decreased, then the equilibrium will shift to increased pressure. And where will it shift to increased pressure? To the side with more moles of gas. So the equilibrium will want to create more pressure, more molecules of gas. It'll go to the left hand side. That's the opposite of this. All right. Now, similarly, another example. Okay. Following this so far? No. When I said externally, I mean externally. I mean to the whole freaking system. Externally, from external parties, for the whole system. And so the equilibrium will then shift to LHS or RHS to oppose that change. That's what I mean. Yeah? Let me show you another example. In this case, we've got methane gas and steam gas in equilibrium with hydrogen gas and carbon monoxide gas. These are all gases. Methane gas and steam makes hydrogen and carbon monoxide. All right? Then I ask you, so if now in this scenario I've got 1 mole of gas here, 1 mole of gas here, and I've got 4 moles of gas here. Now I'll just paste the image also. That for you. So 2 molecules of gas on the left hand side and 4 molecules, 3 plus 1, 4 molecules. So now if I say that if pressure in this case is decreased, what will happen? So if externally the pressure is decreased, what will happen in this case? Yeah, Gringles. I'm actually teaching a class where there are kids sitting in class and they're actually answering. I'm not asking the people on YouTube to answer actually. They're just watching this live. There are actually a whole set of people who are answering the questions. So yeah, on Zoom. This is live streaming from Zoom, so yeah. People do care actually. Right guys? You care, right? I can even name you the people who care. Some guy says on YouTube nobody cares. You got Abdul Hanan who cares, Arisha, Ainur, Mesam, Miral, Ramesh, Rida, Salman. Anyway, sorry, getting back here. Find me the Arisha, give me the final answer. So the pressure is decreased, the equilibrium will increase pressure. Yes. So yes, it will decrease pressure. So the equilibrium will want to increase pressure. Therefore, it will increase the molecules of gas. Therefore, it will shift to the side which is more moles of gas, which is the right side. So it makes more right hand side products. Yup, Arisha, yup, Saad, yup, Rida, yup. That's what happens. You get it now? All right. Now the third factor. That's all clear? ठीक है. Now the third factor is the most interesting one. It's about temperature. ठीक है? Now, before I talk about temperature, this reaction also involves enthalpy changes of a reaction. So you remembered earlier that we've done that enthalpy changes of a reaction can be exothermic and endothermic. Yeah? Exo and endothermic. Do you remember that, guys? And exothermic reactions are, that's something that you got to remember, exothermic reactions are hot and endothermic reactions are cold. That's something that you have to remember. Exo is hot, endo is cold. You guys remember that, right? हमने किया था, हमने एक अदर दिन किया था ऐसा ये भी चैप्टर, अगर याद हो आपको. All right, awesome. Okay, so where was I? Of course. Because why am I repeating this? Because people tend to forget that exo reactions are hot and endo are cold. Now, for equilibrium, this is important. If A and B are written like this, okay, A and B make AB, and I say the delta H is minus 100 kilojoules per mole. What I'm really saying is that it's A plus B becoming AB is minus 100 kilojoules per mole. But AB becoming A and B, the backward reaction, is literally the opposite of this, is plus 100. That's a feature of reversible reactions. That whatever the sign is of the forward reaction, the backward reaction is positive. If the forward is negative, the backward is positive. Yeah. So and that's something that's important, because whenever you're given an equilibria and you've given delta H's, remember they're giving you delta H's to talk about the forward reaction. So if a reaction is given and there's a certain delta H, that's for the forward reaction. So the backward reaction has the exact opposite delta H. Like if the forward is plus 100, the backward is minus 100. If the forward is minus 100, or let's say the forward is minus 250, so the backward is plus 250. You follow? That's something that you guys have to remember. Yeah? So far so good? All right. Yep, okay. The second thing I want you to remember is that when I wrote this, I don't want you to think exo means heat is given off and endo means heat is absorbed. I don't like the word absorbing heat, because in general everyday English, if you are to absorb heat, you will think you're going to become hot, right? That's not what happens in endothermic. They convert heat to some other form. So I don't like to use the word absorb heat. Absorbing means a transfer of heat. It is not a transfer of heat. It is a conversion of energy from heat energy to internal chemical potential energy. Remember, those are the terms we had used. So if a reaction is endothermic, the system surrounding everything becomes cold. So endothermic means cold for both system and surrounding. They both become cold. Remember that. And exo mein, both the system becomes hot and surroundings become hot. Now technically speaking, system doesn't exist. System is everything that you can touch physically is a surrounding. But kids at your age confuse that. So for them, the equilibrium, okay, actual molecules, if they become hot, they'll think it's a system gaining heat energy. No, it's a system converting the internal energy to heat energy. Now, why am I saying this? You need to understand this. The reason I'm telling you this is because obviously if I change temperature externally, the system will have to again do the opposite. Remember, the principle is whatever externally is done, the system does the exact opposite, right? So what I'm saying to you is that keeping this in mind, keeping the fact that exo is hot and endo is cold, so if I give you the same reaction we had seen earlier, nitrogen and 3 moles of hydrogen becoming 2 moles of ammonia, and iska delta H is, let's say, minus 90 kilojoules per mole. I don't know what it is, but let's call it minus 90. What that means is the delta H of the forward reaction is minus 90. And delta H of the backward reaction is plus 90. So the forward reaction is exothermic and the backward reaction is endothermic. And remember, exo means everything becomes hot. Endo means everything becomes cold. Now, imagine you have this equilibrium, and this is just the data so far. Now we talk about the external factors, right? So I have this, I have the principle, yeah. So far I have this information that nitrogen and hydrogen are in equilibrium and they are minus 90 kilojoules. The forward reaction is exo, the backward is endo. Now, to this equilibrium, let's say if externally temperature is increased, what will the equilibrium try to do in terms of temperature? What will the equilibrium want to do in terms of temperature? Step by step, let's follow it, right? So temperature is increased, the equilibrium will try to reduce temperature, meaning it'll go cold. So which reaction is cold, exo or endo? It'll want to shift endo. So it shifts, or we use the word favors, endothermic. In this case, endo is backward, so it shifts left or back. Yeah. On the other hand, if temperature in this case is decreased, the equilibrium will want to increase temperature. So decreasing temperature means that system favors exo, meaning shifts right, yeah. Forward. So far okay? Yeah. So that's what you need to just do. Literally, that's what you need to do. Any questions about this? Thank you. Clear? Awesome. ठीक है. And so basically, if you have, let's say, if A and B becoming AB was plus 50 kilojoules per mole, then in this case, if temperature is increased, what happens to the equilibrium? Which side is favored? And if which side is favored will tell you which which side is favored, and therefore, yeah, what happens to the yield of this? Can you figure this one out? So if A and B become AB and as forward is endo, and now I want to increase temperature, so increasing temperature favors what? Favors decreasing temperature, favors that is in endothermic. In this case, that is where, so the equilibrium shifts where? Right, because that's the, yeah, the forward is endo, Arisha. The forward is endo, not the backward. Bond making is exo, Saad. Bond breaking is endo. Yeah. So if we increase temperature, the system will want to decrease it. Yes. Do not assume that these are atoms and this is a bond making only. I'm just saying some reactant A and B made AB. You know, that's why it's not correct to use them as elements. They're not elements. I just wanted to use something like, you know, like, how do I say this? Okay, so take this reaction. Sodium hydrogen carbonate plus HCl, because that's the reaction I know, that's endothermic. So this delta H is, let's say, plus 80 kilojoules per mole. I don't know what it is, but it's called plus 80. Okay. So now, so you can't look in terms of bond. The bond forming, bond breaking is only applied to covalent compounds when they give you bond energy. Nobody's asking you to debate bond energies right now. It's simply speaking, if the reaction is already in equilibrium, moving, it's already equilibrium, so there's already reacted, it's already made the energy. Then, if a reaction in this particular case, this is let's say if this was equilibrium. It's not, but let's say if this was equilibrium. Then, if temperature is increased, we don't care bond breaking, bond forming. We care about the fact that the equilibrium which already established wants to shift to decrease that change. So it'll decrease, it'll want to make it cold. The only way it can make it cold is by going endothermic side. And in an equilibrium, there are two sides. If one direction is exo, the other is endo. So here, if this is positive, it means the forward is endo. So the backward must be. If the forward is endo, the backward is exo. So if temperature is increased, equilibrium, we want to make it cold. Cold means endo. So where is endo? Forward. So this shifts right. If I had decreased the temperature, the system will want to increase temperature by favoring the exothermic side. In that case, this would have shifted to the left. All right? That's what we have. All right? Okay? Awesome. I guess the last thing, one thing. Sorry. Oh, come on. अब तो ख़त्म ही नहीं किया, पासवर्ड कब करेंगे? No, Excel is not always on the left. You got to look at the data given in the question. The data will always be about the guy on the right. Is that endo or exo? The question will have the delta H, and that will tell you which side is exo and which side is endo. All right? Okay. Now, the syllabus also expects you to know that catalysts they lower activation energy, and therefore the rate of reaction increases. Okay? If the rate of reaction increases, all right? Thank you, Shazain. You're welcome. Oh, thank you. Are you welcome? Now, for equilibrium, it's both the rate of the forward reaction and rate of the backward, both increase. Both increase. All right. Now, what that means is that, because you see, this is what a catalyst does. It just lowers the activation energy for both the forward reaction and the backward. Remember, if this is forward, if this is basically this is the left hand side becoming the right hand side in an energy profile diagram. So if one side is the forward direction, the backward is this way. This is forward, this is backward. So when you use a catalyst, which is this, this is the catalyzed reaction. The syllabus expects you to know that if you catalyze a reaction, both the rate of the forward reaction and the backward reaction increase and will stay equal. And because the rate will stay equal, a catalyst will not affect equilibrium position. So catalyst will not alter or affect an equilibrium position. That's something that you have to remember. So what effect does the catalyst have on rate? Yeah. Here, Shash, dude, can you please let me teach, guys? Everything that is I'm teaching on YouTube, you can get everything here. Why do you want me to go on? It's all here. Use the YouTube. We Pakistanis can't use what we have. We always want something we don't have. I'm teaching right now a class and you're asking me about something else and you're continuously asking me, guys, I have 500 videos of A-levels, man. Use them. What more do you want? It's all covered here. Fight Fang, for some people, even 3 years of past papers are enough. And for some kids, even 15 years are not enough. Yeah, I will do that till next time. I just forget, Saad. I forget. I forget this live chat comment thing. They already have, yeah. I don't have more time to teach, Josh. I teach from 8 in the morning till 9 o'clock at night. I don't have more time, boss, to teach. Anyways. Use the YouTube, please. There's enough videos there. Where was I? So yeah, that's what I have. All right. So that's something that we gotta wrap this on. So the questions generally come combining both rates and equilibrium. Okay. So, and if a factor can affect both the rate and equilibrium, and you should be able to answer both parts. Like if concentration of something is increased, rate will increase and you check the equilibrium. If pressure is increased, rate will increase, check the equilibrium, because you apply Le Chatelier's principle. And then if temperature is increased, rate is increased, but you got to check for equilibrium. Okay. And if catalyst is added, then the rate will increase, but no change in equilibrium. Now these 3 checks are from Le Chatelier's principle. Chatelier's. I can never remember his spelling. I always autocorrect it. Le Chatelier's principle. The one that we said that whatever external factor is happening, the system will do the opposite, will oppose that change. And that's what I mean by this. All right. Check means check, check, check. Like solve it like we just did. Solve it like we just did. What we have, all that we've been doing so far. The last 3 classes were us checking and seeing individually. It was not, there's no universal way every reaction will go forward. Universally, rate will increase if concentration increases. That's always going to happen. But you got to check from the equilibrium which side will decrease the concentration of A. Remember, kya hoga equilibrium? The equilibrium will shift to decrease A. For example, in pressure, it will shift to fewer molecules of gas. And if temperature is increased, it'll shift to endothermic. That's what I mean by check. All right. Okay. That wraps up this 3rd lesson on Equilibria. I wish I can teach tomorrow. Arisha, tomorrow and Saturday I have other classes. That's why Abul takes my class, because I was originally taking only 2 classes a week for O levels. Then I made it 3. Now the external 2 is a bull teaching. I can't do more than 3. Every other batch I teach gets 2 classes a week and videos. O levels I do 3 because you guys, I need to spend more time. But I can't do it. You're welcome, I Noor. I'm thank you for that. I'm glad I could help. All right. My other class is starting right now. I gotta run. It's a 7 o'clock class. I gotta start. All right. You guys are special. I love you all. And I was supposed to do questions today. We took the questions out, but I didn't have time. So yeah. All right. Bye bye. Khuda Hafiz.